Well, we're going to start with the easiest of the derivative rules, which is that the derivative of a constant is 0. So this is super easy to prove if we just put it into our definition of the derivative, right? What do I mean by a constant? I mean a function that's just f of x equals c. So if I do f prime of x, or the derivative of c, then I just plug into here, but look, f of x plus h is just c, right? F of x is just c. So this is just 0. And the limit of 0 is 0. So the derivative of a constant, if there's no variables, it just goes to 0. And of course, that makes intuitive sense to us as well, right? Because if I've got something like y equals 5, right? This is just this line. Obviously, it's a horizontal line. It has slope 0. So it's kind of nice to see that that works out with the definition. It works out exactly what we'd expect. Now, what we did see also a couple of times, right? We saw a couple of different things. If I have, for example, the line y equals x, obviously the derivative is going to be 1, right? Because it's a line of slope 1. So I can say that the derivative d dx of x is 1. I can show that also with this a difference quotient. We also saw a couple of times we took the derivative of something like x squared, got 2x. We took the derivative of something of x cubed, we got 3x squared. Not all of you did all of these problems. A number of you, though, did do this one on, I think, what is it, worksheet 4. There was some problem with the cube. So essentially, we're taking the derivative of x cubed. And if you do this a couple more times, and you can check in your book, right? They do, I think, explicitly x to the 4th. With the difference quotient, you'll get 4x cubed. And so you see there's a pattern here, and that pattern is called the power rule. And we will use that all the time. The derivative of x to the n is nx to the n minus 1. And it's much easier, of course, to do this than it is to do this. Now, we do have to prove this. We just sort of observe this pattern, but in fact, we can prove this. I'm going to leave it for the extra materials, the proof of this. And it turns out that this is true not only for natural number n, but this is actually true for all n, all real numbers n. Which gives us a huge amount of things that we can take the derivative of. You know, so that's kind of nice, right? So I can just go ahead, if I have some stuff, right? If I have x to the 10th, I want to take the derivative of x to the 10th, I just use this formula. It's 10x to the 10 minus 1. So I get 10x to the 9th. And again, very quickly, right, you could go directly from here to here. You don't have to write the 10 minus 1. I'm only doing it because it's new here. And I said it was true for all real numbers n. So what happens if I do x to the 1/3? Well, I use the same rule. I do 1/3 x to the 1/3 minus 1. Right? 1/3 minus 1 is minus 2/3. So this ends up being 1/3 x to the minus 2/3, and you're welcome to leave it that way, or you can put it in the denominator if you don't like negative exponents. I don't mind if you have negative exponents. Some people just automatically put it in the bottom, but you can leave it like that. That's fine with me. In fact, even if the exponent is negative, you can do this. I have the derivative of x to the minus 2. I'm going to get minus x to the 2 minus 2 minus 1, so I have minus 2x to the minus 3. When you've done a lot of these in your head, it's very easy to just go from here to here. Do remember though that it's always n minus 1. So you're used to taking the derivative of x squared and getting 2x. So but remember, if it's x to the minus 2, you're going to go to minus 3. So sometimes if it's a negative exponent, or if it's a fractional exponent, or even better, if it's a fractional negative exponent, like this, it might be better to just write it out to make sure that you're doing it right. So fractional negative exponent, fine. Minus 9/5 x to the minus 9/5 minus 1. Well, don't leave it like that. At least add up the exponents, right? Negative 14/5. Sure. Fine. Very good. Now, let me just point out something here, specifically with this one. If I look at this, notice that here I had a positive exponent and here I have a negative exponent. So if I think about what this looks like, let's just right over here. I had f of x equals x to the 1/3, and then the derivative is 1/3 x to the negative 2/3. And as you know, if you try to do that with this definition of the derivative, actually that would be really bad. Like if it was a square root's not too bad. Cube root becomes a big old headache. Okay, but we don't have to do that anymore. We can just use the power rule. But what I wanted to do is look at these two, look at the graph of those two as functions, and just kind of compare, right? Because we had talked about this in the end of the last chapter. So now we can look again, just kind of to put that back together. If I draw x to the 1/3, it does this thing, right? It's defined at 0, but this was one of our examples of something that has a horizontal tangent, okay? Has a vertical tangent. It's going very steep. So what that looks like when I look at the derivative function-wise is you can see this is in the bottom, right? I didn't write it that way, but you could write it that way. The domain here is all of R. The domain here is everything but 0. I have an asymptote there. So this is the function, but because it's got this vertical tangent, my derivative function has a vertical asymptote. And if I draw that, it does that. Okay, so we saw this we discussed it graphically at the end of section 2.8. Now we can see it from the formula as well. So it's kind of nice to see, and then to see why that happens, because when I use this power rule, I'm basically going down an exponent each time. So an exponent like this, any of these guys that are fractional exponents are going to drop me down. Of course, if it's not like a fractional exponent, if it's just an integer, eventually you'll just get down to a constant and you'll get it to 0. Okay, let me just write that before I'm done. That's the last thing I'll say in this video. Because we can take multiple derivatives, right, with this rule. So if f of x, say, is x to the 5, right? And we talked a little bit about second derivatives at the end of that chapter 2, but we didn't do anything with it because we didn't want to do all this. Now we have a quick rule, and we can go ahead and just add up my derivatives and keep going with my derivatives, right? So 20 times 3x squared, so I can just keep going. And I can take as many derivatives as I want, right? And by as I want, I can take as many derivatives as are defined. And for a polynomial like this, I can just keep going. Eventually, because this is, you know, a whole number, eventually I'll get to something that's a constant, right? And then the next one, by this one, will be 0. And I'm sort of out of space, right? And technically, I could still keep going. I could take the 7th, 8th, 9th, 10th derivative, but I'm always taking the derivative of 0, so I'm always getting 0, okay? But, so you can see, this is sort of behavior is going to happen with a polynomial. I can keep taking the derivative. With the power rule, it's easy. Eventually, I'll get to something that's a constant, and then the next one, and all the rest are going to be 0.